Hey everyone. So before we start part 2 of the series, I think you should take a look at this because it can be confusing for some students to memorize all of this. But if you look a little bit deeper into it, you could see that if you look at the activating groups, it's if you look at the three first line, it's the amines. So amines are activating. So if it's connected to a nitrogen or oxygen, if you look at it simply, you can see that if it's connected to nitrogen or oxygen, it's an activating group, like all of the amines, alcohols, ethers, amides, esters, and the weakly activating are like the R groups and the alkenes. And if we look at the deactivating groups, well, we have the weakly deactivating, which are all of the halogens, and all the carbonyls are deactivating. So like if your benzene is connected to a CO, like a carbonyl, it's deactivating no matter what it is, like aldehyde, ketones, esters, carboxylic acid, acyl chlorides. So it's just simple if you look at it like that. And at the end, we have the like a nitrogen that's connected to four groups, which is positive. So these groups are strongly deactivating. And what you have to memorize is these two, which are the nitrile and SO3H. And the most deactivating group is the nitro group, which is the NO2. And all of the deactivating groups are meta-directing, except for the halogens, which are weakly deactivating. They belong to the OP directing groups. So since we covered that, I think we can begin solving the synthesis problems. Okay, so this is the first problem. Try to pause the video and solve it on your own, and then we can solve it together. All right, so if you take a look at this, the only thing we did here is that we removed this group, which is a carbonyl group right here. And a very good way to remove the carbonyl group in an amide is a reaction called Hofmann Rearrangement. Okay, so this is Hofmann Rearrangement, and it involves using a halogen like a Br2 or a Cl2 with a strong base. And water. So what it does, it removes the carbonyl group and we get our product. Of course, for every problem, there are other ways of solving it. So you could have chosen another way which could be correct. But obviously, I'm just going to use one way in every problem. This is the first one. Okay, so this is the second problem. We have to find out our product, which are A, B, C, D, E, from these reagents on the arrows. So try to solve it on your own, pause the video, and then we can continue. Okay, so in the end we have H2 with a catalyst. So a hydrogenation reaction which introduces the double bond. So A should be exactly the same thing, except without the double bond. So we just remove this, okay? In the second step, we have a strong oxidizing agent. And obviously the only group that we can oxidize is the alcohol. And this is a secondary alcohol. So it will be oxidized to a ketone. By the way, we could have used like PCC here. It doesn't have to be a strong oxidizing group. Again, sorry for my drawing skills, but the important thing is that we get the point. Okay, so now we have a hexanone, which is hexane connected to carbonyl group ketone. And the third step, we have a Grignard reagent, which is known it can attack the carbonyl. So here we have a positive charge on the carbon, and it can attack the carbonyl group. So we get like here we added this group, the R group, so CH3, and the ketone will become, well, it's going to become O minus, because like when this carbon attacks, these two electrons go back to the oxygen, so it will be O minus. But then in the second step, we see here we added an acid, so it will protonate it to an alcohol. All right. So this is C. So to find out D, we have to find out what this reaction is. And obviously there is an acid with heat. So it's an elimination reaction. So we have to eliminate this alcohol. And this is E1. But this carbon here, like we get a carbocation, but when this acid will protonate this alcohol group and it will leave. So we will have, let's just throw it. So it will protonate it will become positive and it will leave. So we will have positive charge here. And this is the tertiary carbocation, so there is no need to rearrange anything. We just have to find out where the double bond is going to be. So it could be here, here, which is the same thing exactly, because it's symmetric, or it could be here. And according to the stability rule, it needs to be the most substituted double bond. So it could be here, or here is the same thing. You can add this product, which would put double bond here, but it's going to be the minor product. So this is D. Okay, and the final reaction it's from organic chemistry 1. And what it does, it's ozonolysis. So what it does, ozonolysis with a strong oxidizing agent. So it's gonna like split the double bond here. So let's do it like this. No, Let's just do it like that. After you split your double bond, you look for hydrogens because you have a strong oxidizing agent here. So this carbon, as we look at it, it has 1, 2, 3, 4 double bonds, so it has no hydrogens. But this one, it has one because there is three, it's connected to 3 double bonds. 1, 2, 3, so it has one hydrogen here. So it could be oxidized further to a carboxylic acid. So here we have carboxylic acid. This is our final product. This is E. Next problem, try to solve it on your own, and then we can do it together. All right, let's try to solve it together. This is a complicated problem. So because some people might say we could add just Br2 in a low temperature, and because the amine, as we said in the beginning of the video, it's an activating group, so it's OP directing. But that's exactly the problem. It can give us Br here and Br here in a high yield. So we don't want that. We just want Br right here. So the way to do that is to add a protecting group. So first, what we need to do is to acylate the amine by using a reactive, like you could use some options, some other options, but the best way, because the acyl chlorides are very reactive with amines, which are strong bases. So the best option would be using acyl chloride. With a solvent like pyridine. And then, like the amine will back here and the chloride would leave. Oh my god, my drawing skills. I really wish I was talented. Okay. Oh. So this is what we get. Okay. And if we remember here, the amides are still OP, but if we look at this, it is now like here we have like a big group. So the ortho position is sterically hindered. So if we add a Br2 now, it would prefer to go on this position, the para position. So now we add the Br2. By the way, here we have exactly the benzene 6 carbons. Sorry about the drawing. So Br2, obviously with a catalyst like Br3. Here we have hydrogen that I missed. Okay, so here we have NH, CO, CH3, and here we have Br. Now we can just use a simple hydrolysis to get our amine back. So by using acid, water, with heat, will give us NH3 here. So in the second step, we add a base. We get NH2 from NH3. So we get this back. Okay, this is our final problem. Try to do it on your own, pause the video, and then we can do it together. Okay, the first thing that might come to your mind is by using just double bromination to a benzene, but this is a problem because once you use the first one, this is a halogen, so this is, despite of it being a weakly deactivating group, it's still OP. So it's like, let's say this is the first one that we added. The second one is going to be either ortho or para or both. So it could be here, like here, here, or para. You're not going to get a meta. So first you need to add to your benzene a meta directing group. So a strong deactivating group. So you need to do the nitration first because NO2 is the nitro group is very deactivating. So you do the nitration first. With an acid like H2SO4 usually. And you get NO2. Then you do the bromination with a catalyst. The NO2 is a meta directing group, so the Br is going to be here. And usually when you want to convert NO2 to a halogen, you need to make N2. So first you need to transform that into an amine by using reducing agent. So you get an amine, NH2, bromide here, and then you can react this amine with Na NO2 as an acid. In a low temperature, like at 0 Celsius. And what you get is a diazonium ion. Like NH2 becomes N2, and N2 is a very good leaving group. So here we have bromide and N2. And N2, like the diazonium ion, can become, like, it has many reactions, and one of them that it can react with CuBr become bromide or CuCl to become chloride. So here we will get our final product readily. Okay, so this is it for part 2. Part 3 will come soon. As usual, if you need any organic chemistry or chemistry help, you can add me on Skype. I offer free help for the students. And you can also comment any questions on this video if you need anything. I will gladly help. And if you find any mistakes or have any notes for me, I would happily accept it. Good luck.